I'd like to do another normal approximation of the binomial problem with you. I think this is one of the more difficult problems in the book. It's very subtle, and I like it very much because it hints at a lot of the ideas that we're going to be covering in the next few chapters, all the way up into chapter 10. So let's take a look at number 2 on page 129. So we've just sent out a test mailing of a catalog to 1,000 people randomly selected from some large database. We know that we're going to go ahead with the mass mailing to the remaining names, provided that we get a response rate of 2.7% or more within the first 2 weeks. So the way to think about this is we're doing some sort of testing. There's a big list, maybe the American Airlines frequent flyer database. We are prospecting for customers, so we go buy 1,000 names from the American Airlines frequent flyer database. We send out this test mailing, and we want to determine whether this is a good list. So if people from the American Airlines frequent flyer database respond to this offer, then we probably should buy more names from this database. Also, if we determine that they don't like what we send out, then we shouldn't buy any more names from the American Airlines frequent flyer database. We'd just be wasting our money. So we've done some break-even analysis and so forth and determined that we need a 2.7% response rate for this to be a good list. Now let's read on. We're asked to find the approximate probability that we will do the mass mailing. Now what that means is that after mailing 1,000 people, we get 2.7% back or more under each of the following scenarios. So part A says, assume that exactly 2% of the population would send in an order within 2 weeks. So let's go over to the sketchbook here. And let's take some notes. So we have an N of 1,000. So we send out 1,000 of these offers at random. And in part A, we're told to assume, I'll just write part A over here, that pi is in fact 2%. Now, notice that this is a bad list. So this is less than 0.027. Therefore, this is a bad list. So we're doing the test to try to determine if it's a bad list. But since this is chapter 7, we know the true probability, and we know that this is a bad list. So what we're really examining in this problem is what's the chance that this test we're doing detects that this is, in fact, a bad list. Now, one other thing. Note that 1,000 times 0.027 is 27. So we need 27 responses out of the 1,000 for us to declare this a good list. Let's go find the mean and the standard deviation. So if XB is the number of responders out of 1,000 that we mail, then the expected value of XB is going to be 1,000 n times pi, so times 0.02 equals 20. So we would expect to get 20 responses back, 20 yeses, and that's well below 27, but there's still a possibility that we'll get an unlucky sample. So let's go find sigma xb. So the standard deviation is equal to 1,000 times 0.02 times 0.98. And if you do the math, this works out to be about 4.427. Now I'm going to go draw the picture of this. This will be approximately normal. N times pi is 20, which is way bigger than 5, so we can use the normal approximation. the mean is going to be 20. So we expect 20 yeses. Now somewhere out here is the value 27. Picture a bar of width 1 centered around that. What we're going to do is evaluate the area in this tail. All right? So this is where we conclude that the list is good. And as we already noted, this is a bad decision. So we've made a bad call. This is the good call region. All right, so we come to the correct conclusion that this is indeed a bad list, as we noted up here. Okay, so what we need to do is evaluate the probability of observing an XB greater than or equal to 27. Using our normal approximation, this is equal to the chance, or approximately equal to the chance, that we have a Z greater than, well, that bar starts at 26.5. So 26.5 minus the mean, which in this case is 20, divide by the standard deviation, which is 4.427. The Z value is 1.47. We go look that up using norm dist. You'll find that the answer is about 0.071. So there's about a 7% chance that we come to the wrong decision about this list. We falsely conclude that it's a good list, we go out, buy more names, and then we discover we'd lose a lot of money on it. There's about a 93% chance that we come to the right decision about this list. If we don't want to live with such a high chance that we'd come to the wrong decision, the solution is to increase the sample size, and that would reduce that probability. Let's go on to part B. Part B says, now assume that exactly 3% would send in an order. So in part B, we're told to assume that pi is equal to 0.03. Now note that that is bigger than 2.7%. So this tells us it is a good list. So this is a good list. We have an opportunity to make some money if we detect that it is a good list with our test. So let's now go find the mean and the standard deviation. The expected value of the number of yeses in this scenario will be 1,000 times 0.03, which is 30. So here's what the picture looks like this time around. Somewhere out here is the mean, which is 30. This time 27 is about here. And I'm going to draw that bar here. So what we're going to do is evaluate this area. So all of this area in this case is a good decision. Everything to the left of here is a missed opportunity. So we missed the opportunity to buy these names and make profit. So we missed the opportunity over here. Well, let's go find our standard deviation. So sigma sub xb will be 1,000 times 0.03 times 0.97. And this works out to be about 5.394. So what we need to do is evaluate the chance again that xb is greater than or equal to 27. Using the normal approximation, this is approximately the same thing as us having a z greater than 26.5 minus the mean, which in this case is 30, divide by the standard deviation, which is 5.394. The z value that we have to look up is minus 0.65. And the answer using norm dist in Excel is 0.741. 0.18 or so. So there's about a 74–75% chance that we come to the right conclusion about this list. Again, if we want to decrease the chance of making the wrong decision, we should increase the sample size, but that also increases the cost of the test. Let's look at the last part. So the last part is now we have a really good list. The response rate is exactly 4%. So what's the chance that we come to the right conclusion? So in part C, pi is equal to 0.04, which is way bigger than 0.027, which tells us this is a really good list. So we have a really good list. The expected value of xb, in this case, will be 1,000 times 0.04, which is 40. So we expect 40 yeses. I'll do the standard deviation right here. Sigma xb will be, well, n times pi is 40, times 1 minus pi is 0.96, and this works out to be 6.197. Let's go draw it again. The picture in this case looks pretty much the same as the previous part, except the mean is now 40, and 27 is sitting way off in the tail. So we need to evaluate this whole area in this region. So what's the chance that we come to the right decision? Well, we need to find the chance that xb is greater than or equal to 27. Using our normal approximation, this is about equal to the chance that I have a z greater than 26.5 minus the mean. So the mean in this problem is 40. Divide by the standard deviation, which is 6.197. The z value is minus 2.18 if you do that math. We go look that up, and the final probability is about 98%, 0.9853, I believe. So in this case, there's about a 98.5% chance that we come to the right decision. So one thing to note about this is that the magnitude of the difference that we're trying to detect influences the power of our test. So what do I mean by that? Well, in part C, we're detecting a fairly big difference. 2.7% versus 4% is a big difference. And we have a whole lot of power, a lot of certainty that we're going to detect that. 98.5% of the time we'll come to the right decision. In the previous part, the magnitude of the difference that we were trying to detect was pretty small. 3% versus 2.7% is only 0.3%. It's going to be really hard to detect that. And consequently, we see that the chance that we come to the right decision is a bit smaller. It wouldn't be a bad idea to find these using binomedist in Excel and get the exact probabilities as well.